We want to focus on the indeterminate form infinity over infinity in rational functions. To find the limit of a rational function at plus minus infinity, we have to divide the denominator and the numerator by x to the highest power of x in the denominator. And it's always going to work. For example, in this case, first we have to find out what is the highest power of x in the denominator. It is 2. So we are going to divide everything by x to the power of 2. Now we are going to do some algebra and simplify, and we get that. Now I would like to recall that we already know that a constant number over x to the power of 2 when x approaches infinity is 0. So this guy is approaching 0, and we get 8 over 1 minus 0, which is 8. The highest power of x in the denominator is 2 because of the x to the power of 2. So we divide everything by x to the power of 2. Simplify the algebra. And we know that the limit of 2 over x to the power of 2 when x approaches infinity is 0. We can take this to 0. And we still get that. But we know that the limit of 8 times infinity when x approaches infinity is infinity. Another example. The highest power of x in the denominator is 2. It's the same denominator as before. We divide everything by x to the power of 2. We get that. Now we know that the limit of 8 over x as well as the limit of 2 over x to the power of 2 equals 0 when x approaches infinity. Because in those two cases we have a constant over a huge number. Let's take these two limits. And we get 0 over 1 minus 0, 0 over 1, and we get 0. If you look at all the examples that we got, we can really actually have a little shortcut in doing the limit to plus minus infinity for rational functions. Let px and qx be two polynomials. Then, the limit of p over q when x approaches plus or minus infinity is what? It's going to be plus or minus infinity if the degree of p is more than the degree of q, because then the dominant part is going to be the polynomial p, and a polynomial at plus minus infinity always approaches plus or minus infinity. If the two polynomials p and q have the same degree, then we are going to get in this limit a finite number. And if the degree of p is less than the degree of q, which means that the polynomial here q is the dominating part, it means that it's much more than the p of x, then it will pull all this rational function to be 0. Moreover, let's say that px and qx can be written as here. Okay, this is descending order when the highest exponent is written first. Then we can be much more exact. Then the limit of the rational function p over q when x approaches plus minus infinity is going to be the following. If n, which means the degree of p, is more than the degree of q, which is m, then we will get plus or minus infinity. If the degrees are the same, and here's the big difference now, which means that n equals m, then the limit is going to be an over bm. And if n is less than m, then we are going to get 0, because it means that the degree of the q is more than the degree of the p. So this gives me a better answer for the case for which both p and q have the same degree. But even more, and this is really useful, that if you want to find the limit of a rational function p over q when x approaches plus or minus infinity, then the limit is exactly the same limit as if you take the limit x approaches plus minus infinity of only an xn over bm over xm, which means that you can only take the highest degrees here, okay? The leading coefficient, as we call it, an times x to the n, and the leading coefficient of the other one, which is bm, and x to the power of m. For example, in this case, we observe that we can just take the limit of this, and we get -8. And in this case, again, we can only take this. And when we take this limit, we can now cancel x cubed, and we get this. And we get -infinity because it's negative times -infinity times -infinity. So it's definitely infinite, and we have 3 times negative, and the answer is -infinity. And in this case, again, we can only take the limit of the ratio of -8x to the power of 2 over x cubed. We get that, which is 0. If you can see, these represent all the 3 cases of the degree of the polynomial above being more, the same, or less than the degree of the polynomial in the bottom.